Well, good morning, ladies and gentlemen. How are we? Let us quickly continue with where or what we stopped on yesterday. After after going through an introduction, why did you bring colored chalk today? Well, after making an introduction, can we? If you don't want to be in this class, you simply march out. I also don't need big numbers. So after looking at the introduction of floating and sinking, where we saw the fact that you can place an object in a fluid, where we saw that you can place an object in a fluid. Let us say the fluid is at this kind of the level in a container or in a bucket. Then you place either a ball, it either floats on water, and this is what we call floating. Then or it goes deep into the water, and this is what we called what? Sinking. So by the end of yesterday, we had gone up to as far as a principle that is going to help us explain all the observations we made. We had seen a principle that was to help us explain the observations we made. And then that principle is called Archimedes principle. Tracy, can you read the principle? Give her a chance to read. When you were taking these notes, you were reading through. Now you can't tell me at this moment that you can't read that one. Oh, partially.
An abstract equal to the weight of the
Young girl, read the principle. Louder, I'm not getting what you're saying. Yes, my daughter here. I'm interested in about 4 to 5 words here. One is holy. Holy. Then partially. You're also interested in that? Immersed. You also you're also interested in upthrust. And then fluid. Whatever the rest is English. Now, I am interested in these words, but you have put in immersed. Me, I was only interested in holy, partially, fluid, and upthrust. That Archimedes, when he was carrying out an experiment, he first and foremost had an object that either he wholly or partially immersed in a fluid. So what do we mean by the term wholly? Any English person here, Zahar. You are Zahar? You are Rehema? You are who? Hajar. Hajar, what is the meaning of the word holy? Holy, not holy. From which word do we get this word, holy? Whole. that when you get a body and you either the whole of it, now like here, the whole of it, you make sure that it is immersed. I explained to immerse yesterday that when you get and make sure that the whole of it is dipped in water, or even if you don't dip the whole of it, but you dip part of it, partially, it comes from the word part. Are we together? So if you either partly immerse it or you wholly immerse it in a fluid. Last time I explained what a fluid is, right? What is a fluid? Yes? Any substance that does what? So particularly there are two examples of all types of the fluids. One is liquid. All liquids are examples of a fluid. Two, gases. Two what? So if you get a body and you either wholly or partly immerse it in a liquid, it experiences this force. This force is an upward force that acts on any body placed or immersed in a liquid or in a fluid. So when you get a body wholly or partly immerse it in a fluid, it experiences an upthrust. But this upthrust it experiences, it is not from nowhere. It is equal to a particular thing, as we are going to see in the experiment. That the upthrust it experiences, the upthrust experienced equals, because it is a force, it is a what? And it is that force we talked about yesterday in the observations, that one, it makes a bucket of water light when you are carrying it from water. Are we together? When you get a tank, fill it with water, then you get a bucket, then scoop water from the tank. When you're carrying that bucket from the tank, it seems to be lighter. What makes it light? Are we together? When you go for swimming, when Dorothy Nakavito, where is she? When she goes for swimming, she feels a little lighter. What makes her lighter? And so on and so forth. So this force is equal to the weight, of the fluid displaced. Of the fluid displaced. Meaning that in our experiment, we shall cater for a provision for when you put maybe a brick or when you put a ball into water, there must be water, because you remember how we determine the volume of an irregular object. Do you remember? Do you remember the experiment for determining the volume of an irregular object? So we said that when you put it into a beaker, you make sure that it has a spout. A spout, such that when you put water up to this level, are we together? When you put water into this can up to that level, and you put a measuring cylinder here, right? If you insert a ball inside here, it will make this water rise or rise. When it rises, it can't go beyond the spout, which means that the one that rises beyond the spout is going to flow to the what? The measuring cylinder. And at the end of the day, when you measure the weight of this ball, I mean, if you measure the weight of this water, if you measure the weight of this water here, you don't need to ask how much force did this ball experience while in water. The moment you have the weight of this displaced water, it will be the upthrust force experienced by the ball. All right. So in other words, mathematically upthrust, according to the notes there, upthrust equals to what? Equals to the weight of the fluid displaced. All right, terms used in Archimedes principle. Term number one, Joan mwisho. Term one is upthrust or buoyancy. Joan, what is buoyancy? In senior 3, we shall look at Newton's laws of motion. One of the laws states that for every action, there is always an equal but opposite what? So when you dump your ball into a can full of water and you dump a ball inside there, this ball, first and foremost, its weight acts downwards. Are we together? First and foremost, the weight of the ball acts where? Now that water or the fluid in which you have dumped the ball, that water is going to give an equal but opposite what? Reaction. So that reaction is opposite to the weight. Now, in this case, that reaction is what we call the upthrust what? The upthrust force or the buoyancy. Are we together? Are we together? So when you fall into a lake, a pond, or a swimming pool, that water that force is going to be exerted onto you by the what? By the water. Are we together? Terminology 2. Obvious. Terminology 2. I am make sure that where we are is where everybody is. If I appoint you at random and you begin looking at me. Actual weight. What is the actual weight of the body? The actual weight of a body, what we call actual weight. Actual weight is that weight that actually the body, you people leave that place, is that weight that the body has. In Latin they say ceteris paribus. You know the meaning? Ceteris what? John. It is called what? Ceteris paribus. Ceteris. You are reading it in English. I am reading it in Latin. Ceteris paribus. Meaning that keeping other factors constant, that the weight of a body, provided that this body is neither in water nor anything is supporting it. So when you get a weighing scale, like if I could carry one from the nurse's office, we bring it here, then we put it on the floor, process steps on it. The pointer will move around the first time, then goes back the second time. What we read there, can we listen? Don't make the girl think that she's too heavy. No. So what you read from the weighing scale, given that you have taken the weight of procy, when procy is in air, what you get is what we call the actual weight. We denote it as W subscript A. Are we together? Are we together? So the weight of a body, when you take that weight and this body is in air, that's what we call the actual what? Actual weight. Next term. Another terminology. Yes, Afandi Ngadia. Good morning. Good morning, sir. Let them do work, Afandi Ngadia. They are late and it is becoming a routine. It is becoming a routine. Let them go to another class. And for your information, I'm not allowing them today. Let them learn. Let them go do work. Another terminology. Apparent weight. What is apparent weight? I'm asking my daughter here. That is one person. What is apparent weight? Wewe, who is seeming to be too academic than the teacher. What is apparent weight?
This is the weight of the body when
Ladies and gentlemen, did you know that you can take the weight of a body when that body is in a fluid? Huh? And if you can take it, initially we have seen the actual weight of a body. If this is a weighing scale, and then you put a body on the weighing what? Scale. Let's say it's a spring balance. One of the instruments used to measure the weight of a body. One of the instruments used to measure the weight of a what? Of a body. And when you put it in air, then you put a body on a spring balance, it will give you a reading that is, say, let us assume it is 50 newtons. So that is the actual weight of the body. However, what will be the reading? What will be the reading of the spring balance when you put the body? When you put the body in what? In a liquid or in water. What will be the weight? If this is a spring balance, and then you make sure that the body is in water. Question, what do you think will be the reading? Will it be greater than this or it will be less than this? So it will be less. Maybe it will be 25 what? Now this weight that you get when you take the measurement of the body or the body's weight, when that body is in a fluid, are we together? That value that you get is what we call the apparent what? The apparent weight. Because you remember I told you that what makes this bucket that you are scooping from a big tank of water lighter? What makes it lighter is the upthrust what? The upthrust force, which means that it is that same force that is going to make this body here, that whose weight was 50 when it was in air, it is upthrust that is going to make this weight to reduce by 25. So it becomes 25 when placed in what? In water. Another terminology. Apparent loss in weight. Christine, read us what is apparent loss in weight. First and foremost, put off the hood. Put off the hood. I've said put off the hood. Read the apparent weight, apparent loss in weight. Ezra, more pieces of chalk. Read louder. Now the word loss, read for us the same terminology. The word loss, those of you who have at least dealt in business, you know. Loss, it is also the difference. Now, in business, it is called loss, isn't it? What is a loss in business? Huh? Auntie, how can you explain to a lay person what a loss is in business? The reduction in the price of a commodity. Take an example. If I bought this duster at 10,000 shillings and I'm a businessman, I bought it at 10,000. Then when I reach the market, I find that I can only sell it at 7,000. That will mean that I've made a what? A loss. A loss is the difference between the buying price and the selling price. So the difference, it must be affecting the businessman. Because the same definition can be used on a profit. Isn't it? That if I bought this duster at 10,000 and I sell it at 20,000, shall I have made a loss or a profit? A profit. So in this case, the apparent loss in the weights, the actual weight and the apparent weight. The difference between the actual weight and the apparent weight is what we call the apparent loss. The apparent what? The apparent loss in what? In weight. Another terminology. Never go here. Never go here. It's okay. We shall. Echaki. Bakiri n'abavubuka. Bakiri n'abavubuka. Omusajja njakuba busimu. Njakuba busimu mbere ekyakalungi. Njakuba busimu naye so mpe ekinene nnyo kawiki kangategate ku bwaya. Kangategate ku bwaya. Okay, so the difference between the actual and the apparent is the apparent law, the apparent loss. Another terminology. I think we are done there. Now, we are saying that the apparent loss in weight equals actual weight minus apparent weight. Therefore, apparent loss in weight, there is a conclusion there. There is a conclusion where? There. My daughter there in the glasses. What is the conclusion saying there? Now, first and foremost, ladies and gentlemen, first and foremost, we say that upthrust equals to the weight of the fluid done what? Displaced. That is the first definition of the upthrust or the calculation of upthrust. If you don't know the weights of the body and you can tell the weight of the fluid that has been displaced, you can find the upthrust. Are we together? Are we together? Yes. Alternatively, upthrust also equals the apparent what? The apparent loss of what? Of weight or in weight. But there are two experiments that we are going to carry out to verify Archimedes' principle. One, we shall use the weights. We get the two weights of the body, the actual and the apparent, then we subtract them. Alternatively, we can also have a body placed in a measuring in an overflow can, then we measure the weights of the displaced fluids. All right. Therefore, if we can compare these two, upthrust either equals to this or equals to that. Are we together? That means that even these two can equal to each other. Take an example. In mathematics, there is a principle. Those who are vibrating, you are risking. In mathematics, we have a principle that says that if you have three numbers, if you have A, B, and C, okay? If you have a number A, a number B, and a number C, but A equals to B, all right? All right? And A equals to C. So what conclusion can you make here? What conclusion can you make here? If A equals B and the same A equals C, so what? So put up your hand if you have a conclusion. So what? Proceed. So what? Yes? Apana. Any other? Yes, Labera? Really? Yes, Leah. Well, make it mathematical a little bit. Yes. You're right. Yes. I've said if A equals B and the same A equals C, so what? Tracy. Tracy, you can't make a conclusion here? Yes. Yes. Therefore, now all of you stand up and clap for this girl here. All of you, nyinyi yote, stand up first and foremost. Remain, sit, wait. I will come up, I will send for a stick. You remain seated, my girl there. I've not said you stretch. Can we give her a hand clap? Once again. Sit down. Now you see how the majority never win. If A equals B and the same A equals C, then it means that B equals C. Now, where is your mathematics? Where is your mathematics? Tracy, you cannot see that if the two numbers are equal to one number, they can also be the same. Where? So the same applies to the upthrusts. If upthrust equals to the weight of the displaced, and we come back. If the upthrust equals the weight of the displaced fluid, and the same upthrust equals the apparent loss in weight, so even this can equal to that. So we can have that also weight of the displaced what? Fluid equals to what? Equals apparent loss in weight of the same body. Factors affecting upthrust acting on the body. What are the factors that affect that upward force? Joan told us that it acts on any body placed in a fluid. Factor number one. My daughter here. Factor one. Density of the fluid. Readers, take us through the paragraph. We are going to look at a demonstration here that the more dense the liquid is, yes, Honorable Minister. Are you a minister? Who are you? Yes, how are you? Who? No, he has the keys. No, I placed them on the table. You guys are in class. So denser liquids exert a greater upthrust force than less densely liquids. And we shall see that by a demonstration. That if we start with fresh waters and put two weights on opposite ends of a meter rule for it to balance, if you keep increasing the density of the water on one side, then you will be increasing the upthrust, so this rule or the ruler will tilt to another end. So we have said that denser liquids exert greater upthrust on a body immersed in it than less dense liquids. E.g., salty water is denser than fresh water, isn't it? Therefore, an object immersed in salty water displaces a greater weight of the salty water. And that displaced one, in brackets they have said it's upthrust, than when in fresh water. Thus the body feels weightless. A body placed in salty water will feel weightless because it will lose too much weight compared to a body placed in fresh water. Factor number 2, my boy here. I've said factor number 2. You man talk like a man. You man gets serious. Can you read factor number 2? I have been reading this word several times. Can you sit down? You man there. Read it. Okay, the rest can we keep quiet? Can you imagine? We don't have boys in this class. Sit down. I appointed you man there, behind the one who was up. Okay, the rest keep quiet. You want to read as well? Okay. Thank you. Now, you see, when you are taking these notes, don't you read? When you come across a word that gives you hard time, what do? You leave it. Today, I had a discussion with a nurse in the morning. Yes. And we were trying to discuss about you people. Yeah. You see, in this class, you're about 100 plus. 128. It is not that all of you are going to finish S4. That's the reality. I'm telling you the truth. Even those who will finish and go to senior 6, not that all of those that will finish will go to senior 6. So we coming here and we run after you is not proper. Me, I studied from a ramshackle school where nobody was there to run after me. I either studied if I wanted or not. The same applies to you. Why would you waste your time coming here if you don't want? You stay home. Yeah. Anybody came at your place and fight and he... You stay home. Then coming here, we struggle with you, and at the end of the day, you roast maize along the streets of Mbaran. It is not that all the people I studied with, senior 4, senior 6, and university, are working like me. However, there are those ones who are even doing better than me, but they didn't go past senior 6. Yes, they are there. So you have two sides to choose. Either you continue in academics or you go and start business. It's a possibility. Than we making noise with you. I also have a family. I have a very beautiful wife. I'm telling you. So I am saying that factor number 2 is If you insert, can we look here? Can we come back? If you get a body and you either fully or wholly, if you get a body and you either fully or wholly immerse it in a container containing water, okay, come out. Carry whatever you were exchanging and come out with it. Stand up with Wewe. First and foremost, you are shabby. Walk smartly. Go join the team out. These are the lumpens I'm talking about. You change your stream from today onwards, right? Go to Semakola Rashidi's stream. Because if the DOS cannot restream you, me, I will. So I'm saying that if you get a body and you wholly or fully immerse it in a fluid, and then you get another one that you partially immerse, let us assume the water is here and the body is immersed to that level there. The question is, do you want to think that the upthrust acting on this is the same as the upthrust acting on this? No. Which one is greater? Which one, here or here? John, this one, let us say this is 1 and this is 2. Which one are you? 1 experiences an upper upthrust than 2. Are we together? This one experiences a greater one than the other. The same applies to, if I have, okay, let us assume all of them have been completely, they have been fully put in water. But a body 1 is small in size. Then a body 2 is big in volume. Which one is going to experience a greater upthrust? A body 2 that is big in volume. Because in calculations, as we are going to see, we shall see it that the body will displace its own volume. You remember an experiment to determine or to measure the volume of an irregular object? That when you insert a body into water, the volume it displaces to a cylinder here is the volume of the what? Is the volume of the what? The volume of the irregular what? The object. So in this case, we said that upthrust is great. Upthrust is great if the density of the fluid is greater. So if you have a meter rule balanced on a knife edge and you put a solid here and then a solid or a weight here, but you place them into a bucket of a liquid. A bucket of a liquid. Of course, this one here is initially, can we look here? The water here is the fresh one. And this one here is a fresh one. Are we together? So initially, when you used fresh, this is A and this is B. At the beginning, if you consider all the buckets to be containing fresh water, the meter rule balances because the weights probably are the same. Maybe the weight of this is the same as the weight of this. So it balances the meter what? The meter rule. And of course, the conditions are you've placed them into fresh and the fresh water. Now, we are looking for which one is going to experience a greater upthrust, which is going to lift it upwards such that the meter rule tilts to one end. Now, if you come at point A and you add salt, right? If you come to a point A and you keep adding salt, such that the more salt you add in water at a bucket A, it becomes more what? More dense. Are we together? Now, when this water gets more dense, remember, initially, before you added the salt, the upthrust that was acting on a body B due to the water was equivalent to the upthrust that was acting to a body A due to the water. But now if you add in salt and you make the water at the bucket A or in the bucket A more dense, are we together? If you add salt here and the water becomes more dense, yeah, the upthrust here is going to increase, and once it increases, it is that force that pushes the body upwards. Are we together? So when it pushes this upwards, what happens to the meter rule? The meter rule is going to tilt. Do you know to tilt? It's going to now fall on the other side of the water in the fresh water. So at the end of the day, you'll have something that looks like that. The water here, I mean the body there, and then this one might even come out of the liquid. Are we together? So that is another explanation or a demonstration that upthrust increases with increase in density of the fluid. All right. An experiment to verify Archimedes' principle. But before, what I've explained is there. What I explained, that actual weight of a body, when you measure it from, are you having the diagram? When you take the weight of a body using a spring balance, while in air, you will get a bigger value. While that body is placed in water, you get a smaller value. When you subtract the two, you will be getting the apparent loss, or you will be getting the upthrust. I don't like what you have just done. And for that matter, pass here. Go the way you are. Don't worry. You will never come back to this class. I don't want stupidity of higher degrees. Never ever. If you see me entering here, you simply go to another class. An experiment to verify Archimedes' principle. An experiment to verify Archimedes' principle. An experiment to verify Archimedes' principle. So I said we are going to look at two setups. Two what? Two setups. Setup one is going to be looking at the weights, the actual, the apparent, and then the apparent loss, and then the apparent what? The apparent loss in weight, which we said actually it is equal to upthrust. Then setup two is we are going to look at now the weight of the displaced what? Of the displaced what? Of the displaced fluids. So let us start with the setup one of the weights. Setup one of the weights. We have a spring balance on which we attach a body or the object, and we take its weight in what? In air. Then we record it as The weight in what? In air. If this is a spring balance, we load it with this object and then it will read a value, which value generally we are denoting it as weight in air or actual weight. Then we get the body on a on a spring balance. We carry the whole thing, put it in water. When we put it in water, of course, we considered an overflow can. An overflow can, that when water reaches the spout, some of it, it will overflow to a measuring cylinder. So we also take the weight here, which we are calling the weight in water. So step number 1, let's get one person to take us through the steps. You are here? All right, take us through the steps. An object, wait. An object, do you people know how to cook? Yes. A few of you know, and the rest they do not know. So I am saying that if they write for you the steps, Evelyn, if they write for you the steps of how to prepare meat, can you read and execute? So you be reading step by step such that these people can. So step number 1, she has said that you weigh. That is it the verb? The verb is a doing word. Now that one is the present something tense. So if it was done sometime back, you say weighed, is it? If you're doing it at that time, it becomes weighing. So this thing was done sometime back. That's why we are saying that is weighed. So take us through. It's spout level. Now this is what they are calling a eureka can, an eureka can, or a displacement can. It's called a displacement can because if you put in a substance or an object and water was at the spout, that water is going to be displaced. Continue.
An indicator of long-way what is placed under the spout of the eureka can.
What I have done exactly. A measuring cylinder, an empty one, but its weight excuse me, its weight must be known, which means that you place it here when you know the weight. Are we together? You place it here if you know the which you can measure first. Are we together? Continue.
The object is then weighed when completely immersed in water using a spring valve, and its weight in water is recovered.
When you put the spring, now initially you held it in air and you recorded its weight WA. Now you carry the whole thing, put it in water. Then you record the weight W subscript W. But this one has its weight W subscript what? Subscript B as the weight of the B. Joan, are we together? You are putting on a face that is, asking. WA is the weight of the body while in air. W subscript W is the weight of the body when completely immersed in water. Then W subscript B is the weight of the body when is the weight of the beaker. All right? Next.
The weight of the plus D is measured and recorded.
Now, after water has been displaced from an eureka can to a measuring cylinder, now you measure the weight of the two things, what and what? What and what? The beaker and the displaced water inside the beaker, and that one is recorded as W subscript B plus D. Are we together, ladies and gentlemen?
Yes.
Are we together? We started by measuring the weight or weighing the body in air. We recorded it as WA. We now put an eureka can and then fill it with water up to the spout level. Then we placed a measuring cylinder or a beaker whose weight W subscript B was known under the spout of an eureka can. Then we bring this setup, insert it in water. We only make sure that the body is inserted in water or immersed. Then we also take the reading W subscript W, which is the weight of now the body in air. But when the body is in water here, water will be displaced and that water will flow to a beaker, right? Now, our beaker, which was empty, currently it has water. So we need to take the weight of now the two things, the weight of the beaker and the weight of the displaced water. Why do we now take the weight again? Who can tell us why are we now taking the weight of the beaker and the displaced water again? Yes? Why are we re-weighing the beaker, yet we weighed it some time back? You are not part of the class. If there is nobody, I'm going to make all of you go out and I enter, I make one person to come. We are not measuring the volume, we are measuring the weight. Correct your answer.
Measure the weight
Over there?
of the body.
We don't have a body there. We are remeasuring or we are reweighing the beaker and the water simply for purposes of now being in position to get the weight of the displaced what? The displaced water. Because in future we are going to use it on the other two equations that we stated. That one, upthrust equals apparent loss in weight, which is weight in air minus weight in what? In water. But also upthrust equals what? The weight of what? Of the displaced water. If we don't reweigh the beaker and the displaced water, we shall not get this. Are we together? Continue.
The weight of displaced water is then calculated W subscript B is equal to W subscript B plus W subscript B.
The weight W only subscript D is calculated. And is calculated from the fact that the weight of the displaced water equals the weight of the beaker and the displaced water, the whole content, but minus what? Minus the weight of the beaker. Yes, young lady, continue.
Since upthrust is equal to apparent loss in weight,
Yeah.
it is calculated from U equals to W subscript B, thus implying
Well, she's trying. Now, we have said that since upthrust equals the apparent loss, since upthrust equals apparent loss in weight, since upthrust equals apparent loss in what? In weight. So that upthrust will be the weight in air minus the weight in water. Are we together? But also from Archimedes' principle, when you measure this weight here, the weight of the displaced water, it will be also equal to the apparent what? It will equal to the apparent loss in weight of the body, which means that if you achieve this and it is equal to this, it will equal to this, you will be doing that, hence verifying what? Hence verifying Archimedes what? Archimedes principle. Because Archimedes principle, now there is a problem among the students. When you tell them to state Archimedes principle, they will state the fact that upthrust equals the apparent loss in weight. That is wrong. The principle states that a body must either be wholly or partially immersed in a fluid. And when it does so, now it is going to experience. What will it experience? It will experience an upthrust. But that upthrust equals to what? Equals the weight of the displaced what? That upthrust the body experiences according to Archimedes does not equal to this. But by mathematics, if we calculate, that's when it will equal to that. So if you are stating the principle, that upthrust must equal to the weight of the displaced what? Of the displaced? Tracy, can you look here? So the upthrust according to the principle must only equal to the weight of the displaced what? Water. So it is found out that upthrust is equal to the weight of displaced water, i.e. U, which we are writing as upthrust, equals weight of displaced water, W subscript what? Hence verifying Archimedes principle. Calculations involving the principle. Now this is where on Monday I will be at the gate looking at every senior to be coming. You must have a calculator. And you know when I say I will be at the gate, I will be there. Shemeril, I will be there. Okay, now let us look at the calculative part of it. The mathematical bit of it. Let us look at how we can calculate all these ones here. Okay, now let us make some few observations or notes about the calculations, then we go to examples. A bullet one. One person, when you all read, you'll overlap. Human. A bullet one. Human talk like a man, hey. Now listen to this boy here. It experiences an apparatus. Where? Up what? I am not getting what you are saying, human. See, even your friends are wondering, where did you go to primary school? Sit down. Yes, Israel.
and apparent loss in weight, which is equal to the upthrust acting on the body.
Yes.
Therefore, upthrust is equal to apparent loss in weight.
That one we have seen it. Upthrust is going to always equal to the apparent loss in weight. Which apparent loss in weight is weight when the body is weighed in air. So upthrust U is going to be weight in air minus weight in a fluid. Bullet 2. Yes, you are Nyakato. The rest keep quiet.
According to Archimede, weight of expressed fluid equals mass of expressed.
Stop there. Now, this is fact number 1. Fact number 2 is generated from Archimedes' pre that upthrust equals to the weight of the displaced what? So these two, we are going to use them several times in our calculations. These two are going to be used several times from our calculations. Now, the remaining work under the facts there is simply reminding ourselves of the senior 1 physics, that weight of a body equals to what? Weight equals to the mass times acceleration due to gravity. So you may not possibly be provided with the weight, but you're given the mass. Can't you find the weight? That's a tick. What about mass, density, and volume? How are the three related? How are the three related? Mass, density, and volume. How are they related? Yes, Leah. From? You come and appear as well. You see people who went to very good primary schools than you who went to MAPS. A school that looks like you want to go and you report me. And by the way, you have my goat, right? The other one. Me, I don't have a secret with a student. How did I get a secret with a student? So volume, change one of the two. So volume equals mass over density. But I wanted you to define, in senior 1 you defined density. How did you define density? How did we define density in senior 1? Density is mass per unit what? Which means that mass equals density times volume. Are we together? So if we substitute this here, are you seeing that? The weight of the displaced liquid or the fluid is going to be the density of the liquid times the volume of the liquid times acceleration due to gravity. So all possible breakdowns can be made in the calculations. Are we together? Then another one is, so this will mean that the upthrust U, if this is the weight of the displaced fluid, this will also be the mass of the displaced fluid. So if that is the mass of the displaced fluid, this will be the density of it will be the density of the what? Then the volume of the displaced fluid. So this means that the weight of the displaced fluid is going to be the density of the displaced times the volume of the displaced what? So at the end of the day, if we substitute this back here, if we bring this back here, we shall have our upthrust as density of the displaced fluid times volume of the fluid, all right? times the acceleration due to gravity. But now, if this is the volume of the fluid, and you remember that when we are finding the volume of an irregular object, do you remember that? The volume of an irregular object equals the volume of the displaced fluid, equals the volume of the displaced what? So this means that the volume of this body that we are going to immerse, this means that the volume of the body immersed in the fluid equals the volume of what? Of the displaced fluid. So all these facts I have talked about, we are going to use them in our calculative examples. Example 1. Of course, we are saying that where necessary, G is a constant. What is the value of G? 10 meters per second what? Example 1, Nyakato. Once again, my daughter, that is a block, not a block. This is a Munyankole. Okay, read again.
A broke wave 10 newtons in air. When completely immersed in water, it weighs 10 newtons. The upslot on the block.
Now this one is a direct example. What do we know, ladies and gentlemen? I said every time you come across a numerical problem, find out what you know versus what you don't know and how the two are related. So what do we know in this case? Weight in air. What is the weight in air? Pardon? 25 newtons. What else do we know? Tracy, I am here discussing and I'm seeing you. I am about to write a report, a bitter one about you and the colleagues. You are displaced. You are put in another stream. And again, from today onwards, don't sit at the back. Am I clear? Are we together? Am I clear? This lesson has ended. The next lessons I will be having with you, make sure that you sit in front here, or else I will make you study while kneeling down. What else do we know? Weight in water. What is the weight in water? 10 newtons. What are we supposed to find? The upthrust U that we don't know. So what do we know about upthrust when we know the weights in air and in water? What do we know? Yes. Come and do it. Is he correct? Thank you. Now, one thing that you need to do as people who are doing science, mathematics, or the physics, what is this now? Huh? What is this, honestly? Is it an equation? Is it anything? What is it, a statement? Avoid this. Write an equation. Start and say upthrust equals weight in air minus weight in what? Here I don't give a mark because this is nonsense, rubbish. So write an equation, a complete one. Example 2. Hey, that was part 1. Yes. Part 2 asking for volume of water display. How do we get the volume of water displaced? Now, in this case, can we look here? In this case, and you are serious, continuing. I've said, can we look here? You are stupidly continuing with your writing. So Roman 1, we are supposed to find the upthrust, which we have. Roman 2, we are supposed to find the volume of the displaced what? Water. Who has an idea of how we can find the volume of the displaced water? Yes, Labella. You want to do it here? Come and try. Labella, we don't have the volumes. You are correct by formula, but according to what you know, you will not get the answer. Thank you so much. Any other person who can tell us the hint? Yes, come and take us through. Can you tell the girl the answer? Can we give her a round of applause? Give her a better than that. You know, for us, we can teach you, but we can't teach you how to think. The facts that I made, the observations that I made, the notes that I made first, the notes that I made first are the ones that can lead you to the answer. If you know the upthrust, it also equals using Archimedes' principle. Using Archimedes' principle, then you substitute for the mass, for the weight as mg, then you substitute for the mass as rho v, and then the density of water is a constant. Then you continue and get the answer. I beg to stop there.